I apologize for the sniffling. This is not a tissue. This is a wipe that I used to clean my area when I came into the room. I do not have COVID symptoms. I checked the little app, and I will demonstrate to all of you that today I have a green passport to be here. Here it is, Samantha. There's my green passport. But I think I've got allergies, and it's kind of yuck. It reminds me of this one time in the pre-COVID era. I think it was my first time teaching here, it must have been winter of 2012. And I was teaching sophomore organic to non-majors, and I was having an allergy day, and this is gross, but we're all friends. I mean, my nose was dripping, right? And my body was working overtime to make those mucin proteins that absorb water and create snotty hydrogels. Well, a student came to my office, and we were looking at her exam, and as I was looking at it, I dripped snot on her exam. It was just horrible. So it's great that the mask is in place so that I don't have to deal with that particular problem. I hope I'll be able to get through this. Okay. So we are spending more time in Chapter 14 than I envisioned. That's okay. We're going to adjust whatever comes downstream. There will be topics I originally intended to get to that we won't get to, and that's just fine. I really want to make sure we have a strong basis in quantum chemistry before we move on to talk about reactivity, molecular reactivity. So we mentioned last time, now that we've talked about how the process of maybe solving for a wave function based on our understanding of the Hamiltonian, we now need to identify some constraints to put on our guess for what the wave function is going to be. And the Pauli Principle puts a constraint on us. So I realized as we began talking about this yesterday that I didn't do a very good job of defining some of the terms. So I'm going to try again. This first thing, total wave function for a molecule. What do we mean by that? You might envision this as a wave function that contains a description for all of the electrons in the molecule. Remember, I think a few days ago when we talked about, let's see, was it in this class? No, I think it was our second class when we talked about the various terms in the Hamiltonian. We can include all the electrons in our Schrodinger equation and get a wave function that describes the overall molecule. Yeah, go ahead, Dakota.
So then is the square of that molecular wave function the probability of finding all of the electrons all in the same space?
Yeah, so the question is, would the square of that molecular wave function be electron density over the whole molecule? Which is frankly something we want to know.
So it's just electron density, not the chance of finding any electron in particular.
Right, overall electron density. Which is something we want to know. Upstairs in my office before I came down here, I was playing with the program Gaussian to generate some electrostatic potential maps for some simple arenes that are interesting for some research that we're doing. And these are the kinds of things you can get out of the wave function that the computer will do for you. But for the kind of computations we're going to talk about, we're going to make a simplification, and that is that the total wave function for the molecule is going to be equal to the individual probabilities or the individual wave functions of each electron in the molecule multiplied by each other. Okay? So each of these terms that I'm putting here represents a 1 electron wave function. Hold on. At least so far as we've been talking about orbitals, we've said each orbital can contain 2 electrons, but they have to have opposite spin. All right? And that's actually the Pauli principle. But it turns out a more fundamentally correct way to talk about this is to say the wave function represents the spatial distribution and spin of 1 electron. And you have as many wave functions as you have electrons. So this, for example, wave function A actually contains a spatial part and a spin part. And that has some interesting consequences for us. We could say, but before we move on, I want to point out that defining the total wave function of the molecule in this way requires us to consider each electron as independent of the others. What do we mean by that? Well, the Schrödinger equation accounts for electron-electron repulsion, but the way we're going to handle that computationally for the simplest methods is just to say each individual electron feels repulsion from the general field of electrons that surround it. What this doesn't take into account for is what is called electron-electron correlation, which describes how, with the same spatial distribution, electrons will move so as to not be near each other. And that will lower the electrostatic repulsion. It's very difficult and time-intensive to calculate that, and so we're ignoring it here, but it's not a particularly good idea to ignore. But that's okay. I'm all in favor of useful but not that great ideas. So because the wave function overall of the molecule represents something related to probability, think of it this way. If I flip a coin and I want to know what the probability of a specific result is at the end, say I want to know what the probability of getting tails, heads, and tails from a coin flip, the overall probability is going to be equal to the probability of getting tails, which is 1/2, times the probability of getting heads, which is 1/2, times the probability of getting tails, which is 1/2, right? Probabilities are multiplicative. So we can do that with wave functions too. And again, that just requires us to make the assumption that the electrons are independent probability events. What I just described to you for flipping the coin would not be true if I flipped the coin and it was tails and then that influenced the outcome. Which, frankly, you can convince a child that what you flipped in the past predicts what's going to happen next, which it does not. Anyway. So now I want to just mention how we're going to write about electrons, about wave functions, 1 electron wave functions for this part of the chapter. We're going to split the 1 electron wave function into a spatial part, which oddly enough we're going to write the same way. And I'm just doing what your text does. I'm sorry, it could have been a better way to do it. Times a spin part. And we're going to define 2 spin wave functions, alpha and beta. Now, we're not we don't know which one is up and which one is down. I'm not sure we can know that. We just know they're different. Okay. So the wave function for an electron in spatial orbital A with spin alpha is equal to the product of those two things. Yeah, Dakota, go ahead.
Does spin up and spin down have some physical significance, or is it just arbitrary, like positive and negative?
Does spin up and spin down have some physical significance, like positive and negative charges? Well, we only know, if you really think about it, we don't know that positive is positive. It's just opposite of negative, right?
Yeah, I remember reading in Physics 220 that it was a convention defined by Ben Franklin.
Okay. Convention defined by Ben Franklin. Yeah, that weird thing in physics where current is the movement of positiveness, even though it's the electrons that move. Well, who knows what the physicists are doing, and good old Ben Franklin influencing us still today. All right. So notice then that two electrons might have the same spatial distribution but have different spin. Okay. And a couple of things we need to deal with if we're going to allow these spin wave functions to exist. First, if we ever end up integrating a spin function times itself over all space, that's equal to 1. But if we ever end up integrating a spin wave function multiplied by the opposite spin, that's 0. That is a way of saying the two spin states are orthogonal. Okay. And that'll become important to us a little bit later on. But that's sort of another way of saying that two wave functions, that's sort of a way of explaining that a single electron can't have both spins. Okay, yeah.
So I think I can visualize the physical space as wave function, but I've always kind of seen spin as a like +1 -1.
Uh-huh.
What does it look like as a wave function? Like, what does that mean?
That's a great question, and the answer is I don't know, and your text doesn't explain it. In my mind, though, spin is constant, right? And it's either, and for electrons, it's half integral values. It's either 1/2 or -1/2. So, with the exception that the two spins are orthogonal to each other, I think you could think of them as just constants. I mean, they're not exactly integers because we can multiply 1/2 by -1/2 and we get a number that's not 0. In this case, you don't because the spins are orthogonal to each other. All right. Another assumption or another detail that we're going to make here is that let's suppose wave function A and wave function B represent two different spatial wave functions in the same molecule. Those two wave functions will be orthogonal to each other. That means that different molecular orbitals in the same molecule don't overlap with each other. In the same way that the two p, x, y, and z are orthogonal to each other and don't overlap. All right. So let's go back to the Pauli principle. Now we've defined some terms. What we have said is that the total wave function for the molecule must be antisymmetric with respect to some switcheroo operation where we change the coordinates of any one electron. Okay? Now, let's suppose that we have a molecule where there are only 2 electrons, and therefore 2 one-electron wave functions. One molecule with 2 electrons. Okay? And for fun, we can suppose this is hydrogen. Now let's say that since we know what the molecular orbital for hydrogen is and what it looks like, we're going to say these 2 electrons have the same spatial distribution, but opposite spin. What would it look like if we want to try to construct our total wave function for this molecule? Well, and let's just call that spatial distribution psi A. All right? I'm going to do something now here that your text doesn't do. Your text tries to keep it general, but then it gets somewhat confusing because the A's and B's and C's are all over the place, and it's not clear whether it represents the same spatial distribution or a different spatial distribution. They're trying to keep it simple. I will provide another take on it. My notes that are posted online follow the book very closely, so hopefully between all of that you'll get a picture of what's going on. All right, so the first electron, and we'll label that electron. We'll give it a name. We'll call it 1. All right, the name by which this electron shall be known in our discussion is 1. And it will have spin alpha. Okay, so what I just wrote means is the spatial and spin wave functions for electron 1. Okay, then let's say because we're operating on this hypothesis that the total wave function should be some kind of product of the individual wave functions, let's just now put the second electron in. It has the same spatial distribution A, but it has spin beta. Okay? Now, our question is, does this description of the wave function for the molecule obey the Pauli principle, which is required for fermions or electrons? Have we written something that's physically reasonable? Well, to figure that out, what we're going to do is we're going to put the wave function through the old switcheroo operator, except that's operaptor. That's kind of some kind of bird or dinosaur that operates on things. Okay. And then we're going to ask, do we really get the negative of the total wave function? So I'm just going to write down again this product of individual spatial and spin wave functions. Remember, this is a single molecule, 2 electrons, same spatial distribution, opposite spin. Now we're going to switch places 1 and 2. Right? So all we need to do is say, okay, now I'm going to put electron 2 in spatial distribution A and give electron 2 spin alpha. And then I'm going to put electron 1 in spatial distribution A with spin beta. Are those opposite each other? If this worked, all I would need over here is a negative sign. But it doesn't work. Go ahead, Kim.
Alpha and betas don't intrinsically contain a negative sign somewhere, even though they're spin.
No, alphas and betas don't intrinsically contain a negative sign. These two situations are not opposite each other. Okay, in other words, when we switched, we didn't get the negative. Now, you could argue that they're probably equal to each other because we don't know one electron from another. That's fine. But with respect to the switcheroo, it's not opposite. Now remember, the postulate that the switcheroo has to make it opposite, there's no justification for that in your text. I looked it up, and it is it is something derived from, quote, relativistic quantum field theory, which sounds interesting enough to let you go explore it on your own at some point in the future. I'm 20 years on in this business, and I don't have any idea what it means. So there you go. Ask Dr. Seavey. He probably knows. Okay, so what we've learned is formulating the total wave function for a molecule as a simple product of individual one-electron wave functions does not obey the Pauli principle. All right. So what are we going to do? Let's try something else. And we'll try a different formulation of the overall wave function for the molecule. Okay, and this is what your book suggests. And I'm not sure who first thought of it. It's not like it falls obviously out of the discussion we've been having, but it does work, and so it doesn't matter where it came from as long as it's true. Truth is truth. All truth is independent to act in the sphere in which God has placed it. So what if we instead formulate the wave function for the molecule this way? Spatial distribution A, spin alpha times spatial distribution A times spin beta for electron 2. And I'm sorry, let me just fix that. Electron 1 in spatial distribution A, electron 1 with spin alpha times electron B. Oh, dang it. Sorry, guys. Times the spatial wave function for electron 2 times the spin function for electron 2. That's what we just did above, only now we're going to put minus the following. Okay. A difference between products. Go ahead.
So, does that somehow mean that electron 1 is both alpha and beta?
Does that sort of mean that electron 1 is both alpha and beta? That is a really good question, and it turns out, and maybe I'll just read you something that I found online, trying to understand what all of this means. But what we're coming to is this idea that because electrons have to be indistinguishable, we can't assign a specific electron to any specific spin orbital. Instead, we construct functions that allow each electron's probability distribution to be dispersed across each spin orbital. The total charge density described by any one spin orbital cannot exceed 1 electron's worth of charge, and each electron in the system is contributing a portion of that charge density. So yeah, we know the orbitals are there, we know the electrons are there, we cannot know which electron goes in which orbital, and from a certain point of view, each electron contributes a portion of each orbital. It's bizarre. And I'm not sure what that physically means. It may be more a function of what we can and cannot know about molecules. So it's a really good question. Okay, so we've written the wave function this way. Now let's try the old switcheroo. Except I can't spell or write clearly. I'm sorry. Switcheroo equals, and just to save me time but not you, I will copy and paste, only we're going, oops, too big of an eraser. I'm going to just switch where electrons 1 and 2 are. Okay. I want you to look at those two expressions, psi total versus psi total switcheroo. What's the relationship between the two of them? Take a look at that for a minute and see what you can find.
Sorry, Josh, this is probably a dumb question.
Nope,
Why-
not a dumb question, but go ahead.
Weren't they switched in the second one?
Oh, Kim, thank you. I just forgot to, so thank you for that. Is not a dumb question. That is an astute observation. All right, now it's better. Thank you. I'm so sorry. Okay, so what's the relationship between those two? Can you see that they're opposite?
Yeah.
This term here, which is negative, I guess I should use the pointer so Samantha can see. This term here, which is negative, is positive up here. This term here, which is positive, is negative up there. So, y total equals the opposite of y. That's not y, that's psi. Total wave function equals total wave function having been switcherooed. Therefore, it obeys the Pauli principle. So any guess that we're going to make for the wave function of the molecule has to have this basic form in order to obey the Pauli principle. Now we've just done it for 2 electrons, okay? But of course, this needs to be true even if you do it for many electrons. So one of the things that your text points out is that this formulation of our wave function is actually equal to the following determinant. It's okay if you don't remember what a determinant is or why it's important, as long as you know that if you want to find a determinant, it equals A times D minus B times C. You got it. You're good enough. Go ahead.
Yeah, and for bigger matrices, your options are to do cofactor expansions or something.
Yeah, for bigger matrices, your options are that you can do it for a 3x3 matrix, pretty straightforward. For options bigger than that, you have to either use a computer or do lots of manual things where you reduce bigger determinants into smaller determinants. If you really want to do that, that's fine. But it's so easy just to ask Mathematica, what is the determinant of this matrix? And it will tell you. All right, so I'm going to just represent what our formulation for the overall wave function, highlighted above. I didn't mean for those underlines to be there. And I'm having to copy things down carefully. Make sure I get this right. So on the first row, we have the contributions from electron 1. And on the second row, we have the contributions from electron 2. Remember, in our hydrogen molecule, both of these electrons have the same spatial distribution. They just have opposite spin. But we're sort of accounting for all the possibilities here. And you'll notice if we take this determinant, it's the A position term times the D position term, which gives us that portion. And then we subtract the B position term from our C position term, and we get that. Okay? Wave functions that are defined in this way are called Slater determinants. And occasionally you will see when you're setting up a computation, you will see an option to use a basis set that has the abbreviations STO in it. and that refers to Slater-type orbitals, which means those orbitals are formulated as determinants. Okay? So, of course, we could expand this out sort of infinitely, but... And I don't think you should write this down because I think it's horrific and horrendous. But I'm just going to copy it down here. And it's in your book. I'm going to make a few changes. I'm going to assume that we have a molecule where the total spin equals 0, and you have pairs of electrons with the same spatial distribution, but opposite spin. Okay? And so you can formulate an n by n, or whatever, a square matrix and find its determinant, and that will give you a wave function that obeys the Pauli principle. Now, I told you we were going to get to how we know that the Pauli principle tells us that two electrons can't have the same spatial distribution and the same spin. Go ahead.
So for this, you have to do psi A1 alpha 1, psi A beta 1, and then you keep alternating between
Yes.
alpha and beta.
Yep. Yep. You keep alternating between alpha and beta.
Yes, because each orbital fills up with 2 electrons.
Right. Now, here's an interesting property of determinants, okay? This is weird, but it's true. I'm going to demonstrate it with a 2x2 matrix. If 2 columns, is it 2 columns or is it 2 rows? Oh, brother. If 2 columns of the matrix are of the determinant, oh my gosh. If 2 columns of the determinant are equal to each other, then the overall determinant goes to 0. So let's imagine A, B, let's see, no, it would be 2 columns equal to each other, A, C, C. A times C minus A times C equals 0, right? So what that means is if I took this first column of my matrix, which describes having spatial distribution A and spin alpha, and I copy it here and say I'm going to have 2 electrons with spatial distribution A and spin alpha, guess what? The whole determinant goes to 0. The wave function collapses. Nothing can happen. Okay? Yes?
So, maybe this just hurts my head. So basically,
It's okay.
the Pauli principle comes from some invented thing that we said had to be true. Like, we determined that the wave function has to be antisymmetric because electrons are fermions.
Right.
And if you make 2 of the columns the same, then the Slater determinant goes to 0, and so they can't have the same spin and spatial distribution.
Exactly. Yeah. So far, Isabella, go ahead.
So are Slater determinants the only kind of wave function that satisfies the antisymmetric with respect to space?
That's a great question. Are Slater determinants the only kinds of wave functions that satisfy the Pauli principle? I don't know. I do know that you can actually do quantum mechanical calculations without even knowing or using wave functions. Something called density functional theory that your book talks about briefly, and that I know how to set up in Gaussian, but I don't really know what it means. Everything about this class would be better if Professor S were teaching, I think is the... But I want to come back to Kim's question. Where does the familiar formulation of the Pauli principle has been 2 electrons per orbital, but with opposite spin? Has to be, right? Now we're understanding that that's not the basic rule. Rather, the basic rule is a couple of steps back, which is electrons are fermions, the total wave function of the molecule. They have to be indistinguishable from each other. If we move one and switch 1 and 2, that's going to make the total wave function has to be antisymmetric with respect to switching the places of 2 electrons. And a consequence of that is that if 2 electrons have the same spatial distribution and the same spin, the wave function goes to 0. Okay. All right. Other questions? Yeah.
I think the comment, maybe you already knew, I'm not sure if you knew this, but density functional theory is where we just calculate the electron distribution directly.
Okay.
We already said going through the wave.
So density functional theory deals with the overall electron density of the molecule, from which you can back calculate out a bunch of other things. Is that the idea?
Yeah.
Okay.
It reduces the number of coordinates.
Yep. DFT also, I believe, accounts for correlation, electron-electron correlation, which is pretty cool. Okay. So we now have our description of the wave function for the molecule. Now we're going to apply the Hamiltonian to that wave function of the molecule, and we're going to start getting some results. I will point out that if you run calculations, you will see the option to use what is called an unrestricted wave function, and this is where you have one electron wave functions with defined spatial distribution and spin. And then you could also make it simpler and use a restricted wave function where you have a wave function that contains 2 electrons with opposite spin. If the overall molecule has a spin equals 0, you can set up your wave function in a way that still obeys the Pauli principle, but does not have to deal with the spin portion explicitly. If you are working on a molecule that has unpaired electrons, you have to use the restricted wave function method. And yeah. Let's see. Okay. Anything else? So I'm going to introduce a method for dealing with solving for individual wave functions and energies. And that's called the Hartree-Fock equations. So this is how we're going to now, given our guess for the wave function of the molecule, we're going to find individual wave functions for each electron and individual energies for each electron. Okay. So it turns out that, and this is a connection that's difficult to see, because we're describing our wave function as a determinant, we're actually going to be able to split our overall Schrodinger equation for the molecule into separate equations for each electron that we have. Okay. At this point, rather than me try to scrabble down what's on my notes, and rather than you trying to scribble that down as well, I'm going to copy some things from my note file that should hopefully facilitate our discussion. If you feel like you need to copy down things and write them in order to know that you understand them, I am sympathetic to that. I feel exactly the same way. I I just think our class time is perhaps too precious to spend too much of it doing that. And so we're gonna talk about this. The Hartree-Fock equations have a representation for what the Hamiltonian is. It's based on those three terms we talked about, right? Kinetic energy, electron nucleus attraction, and electron-electron repulsion. And so there are sort of three different terms in the Hartree-Fock operator. Each electron is going to be distinguished by a label from 1, 2, 3, and so on to n. And there's going to be as many individual Hartree-Fock equations as there are electrons. Psi with the subscript I stands for a one-electron wave function from the Slater determinant, where I has a label from A to B to C to N. Spin terms we're not showing explicitly, but they're implied. J, little j, represents all the other one-electron wave functions. Okay. So for if I equals, if we're talking about wave function B, the HBB term would be here, and then we would have n j terms. We'd have a j term for BA, a j term for BB, a j term for BC. J accounts for one electron-electron repulsion. So you've got all possible combinations. K is a little bit unusual, and it's physically hard to describe, but it's responsible for Hund's rule, which is that if you have orbitals that are of the same energy, you fill them up each with one electron parallel spins first before you start making pairs. And we'll talk briefly about where that comes from. Yes?
Is that K term also like responsible for electron-electron correlation? Like, would they...
Is it responsible for electron-electron correlation? I think it's part of it, but electron-electron correlation refers specifically to the fact that electrons can move in response to each other, even independent of the fact the spin definitely counts, but also charge repulsion. And so I think electron-electron correlation refers to the charge repulsion you don't take into account when you say, okay, electron 1 experiences the field of all the other n-1 electrons. That's a static field. It's a self-consistent field. It doesn't change anymore, when that's not actually how things are. Go ahead.
And that's the formula for HII?
That's right. So the HII is...
And there's one Hamiltonian for the whole molecule then?
So we're gonna use these individual Hamiltonians to find out the individual wave functions for each wave functions for each electron, and then we'll know everything we need to know to figure out the overall wave function for the molecule.
Okay. And in the original Hartree-Fock operator, then we had the Coulomb and exchange forces under the J index?
That's right. So in HII, you have kinetic energy of the electron and then Coulombic attraction between the electron and the nuclei in the molecule. So that's sort of the simple part. J, we will see, represents electron-electron repulsion, and K represents this weird thing called exchange, and it comes from the fact that our wave functions are determinants.
So that sum there is to include the influence of all the surrounding electrons?
That's right. The sum here is to include the influence of all the surrounding electrons on electron I.
And HII is not influenced from other electrons?
No, HII is only the kinetic energy of electron I and its Coulombic attraction to the nuclei.
So yeah, we're pretty much leaving the other electrons out of the picture except to give forces?
That's right. And what we do, we're not allowing the other electrons in that instant that we're calculating it to move in response to the one that we're looking at. What we do is we iterate until the answer stops changing, and then we say that the electron exists in a self-consistent field with all the other electrons. but that doesn't take into account electron-electron correlation. All right, so HII is called the core integral. We've described it as kinetic energy plus Coulombic attraction between the electron and the nucleus. Then K and J derive from the electron-electron repulsion term in the Schrodinger equation. So electron-electron repulsion was, okay, the repulsion between electrons A and B, the repulsion between electron A and C, and so on, which seems simple enough. So J represents that. But
Or K as well.
J represents electron-electron repulsion. K is weird.
Okay.
And based on the way your text describes these equations, it was not clear to me where K comes from in the math, other than by saying that the determinantal nature of the wave function, which we're using to abide by the Pauli principle, generates this term K. So that math connection is sort of fuzzy to me.
Okay, so when you put up there J and K are derived from electron-electron repulsion, you're just kind of guessing that K also.
No, K comes from that term, but as far as I understand it, these Hartree-Fock equations each deal with the individual wave functions, not with the overall wave function for the molecule. I think Hartree and Fock put the K term in there to account for the electron-electron repulsion, and then K comes about in part because of the overall formulation of the wave function as a determinant. Let me show you this just really briefly. So let's go back to, let's imagine a wave function for a molecule with only 2 electrons. We'll call the 2 spatial wave functions I and J. And there's electron 1 in I and electron 2 in J, and we've had to formulate this wave function as a determinant in order to abide by the Pauli principle. Okay, so now let's put this wave function for our molecule through the Schrodinger equation, and let's figure out the overall energy that we're going to get from the term of the Schrodinger equation that I've just shown you, this electron-electron repulsion term. Okay, to do that, we would take the electron-electron repulsion operator, which is, let's see, E squared over 1 over IJ. We're going to we're going to apply that operator to our determinant, and then we're going to multiply what comes out of that by the complex conjugate of our determinant, and that should give us the energy from electron-electron repulsion. So remember that with integrals, anything constant we can factor out. So we're just going to put that in the front and forget about it. And we're going to simplify the notation here just to save ourselves time. We're going to say that this determinant is equal to ij minus ji. Is that a little bit easier-ish? All right, and then we have constant K. and we'll need to talk about this next time. But if we take the IJ product, apply the operator to it, and multiply it by IJ, we get the Coulombic repulsion between electrons I and J. On the other hand, if we take the repulsion operator and apply it to Ji, and then multiply it by Ij, we get something different. We get something that's like the repulsion between the two electrons if they switched places. And it's called an exchange integral. And we'll talk a little bit next time about what that does for us. All right, happy Friday. See you guys next time.